When we describe Edwards' short descent, Fermat's little theorem was used as the first step, but no detail was provided on how to get the equation a squared plus 1 equals p times k, where a is smaller than p. Fermat's little theorem states that p divides a raised to p minus 1 minus 1 if p and a have no common factor bigger than 1. That is, if they are co-primes. See a link below for an introduction to the topic. If p is a prime of the form 4n plus 1, then algebraically it can be factored as shown, where the second bracket is in fact a sum of two squares. Some values of a ensure that p divides the sum of two squares of the second bracket, while other values don't. The first ones are non-quadratic residues of p, while the second ones are quadratic residues. Obviously, you try the smallest values of a to check divisibility. It's easy to show that quadratic residues of p let p divide a raised to 2 times n minus 1. That's because there's a x allowing that x squared plus minus a is equal to p times k. So replacing a in the first bracket, you got this expression. If p divides that expression, that means that it should divide x squared raised to 2 times n minus 1, which actually is 4 times n, which is p minus 1. And so we end up in Fermat's little theorem, thus ensuring divisibility. And so all other a's that don't have a corresponding x are a quadratic non-residue, which ensures that p divides a raised to 2 times n plus 1. When p is of the form 4 times n plus 1, Fermat's little theorem gives us a starting sum of two squares to work with. The usual next step is to note that we can rewrite a raised to 2 times n and then express a raised to n as this. We apply that. And so p divides all terms but r squared plus 1, so it should divide that sum of two squares too. In doing so, we found the smallest sum of two squares that p can divide. That's the logical way to deal with that. Yet, just for educational purposes, we can reach that conclusion through an infinite descent. The idea is to present the method of infinite descent as easy as possible. Usually, how it works is explained either when showing that the square root of 2 is irrational or when proving Fermat's last theorem for fourth power. Well, here's another straightforward way to grasp how a Fermatean-like infinite descent works. You start with that initial equation a raised to 2 times n plus 1 equals p times k sub 1. You just express p as the difference between a raised to n and m sub 1. Then we can add and subtract m sub 1 squared to the initial equation and regroup as those brackets shown. On the right side of the equality, we replace p with a raised to n minus m sub 1. As p divides the first bracket, as that can be factored as the product of the sum and difference of a raised to n and m sub 1, and we already know that p divides the right-hand side of the equality, then p must also divide n sub 1 squared plus 1. That sum of two squares is smaller than a raised to 2 times n plus 1, and so we have in fact a descent. That step can be done again and again until we reach the smallest sum of two squares that p can divide, where n sub z is bigger than 0 but smaller than p. There we have in fact an infinite descent. Here we have an infinite descent applied to prime 53. It's really an infinite descent, not practical at all. But this really infinite descent can be shortened simply by noticing common factors of the terms, and that when both squares are odd, then it is divisible by 2 and so can be reduced to. Doing so, we can shorten the steps from 154 to only 10. Yet, is still too long, given that 53 is a small prime. So in the next sections, we'll explore faster infinite descent procedures.